Now we will prove the second part, which means theorem D. In theorem A, we have proved two different parts. One is Bessel's inequality for finite cases, and the second part we have proved for finite cases. But now we will prove for arbitrary orthonormal set. So this theorem D, this says if EI is an orthonormal set in a Hilbert space H, EI, this is orthonormal set in a Hilbert space and X is any vector in H, then X minus X EI to EI is perpendicular to EJ for each J. So this theorem says if we subtract all the components of the vector X in different mutually perpendicular directions from X, then the remaining vector is perpendicular to EJ, which means the remaining vector has no component in the direction of EJ. So we have proved this theorem for the finite case when this is a finite orthonormal set. So again we define here the set S, which is collection of all the vectors EI for which X EI is non-zero, which means all those EIs for which X is not perpendicular to EI. Then we know that this S is either empty or a countable set. So when S is empty, we define this summation X EI to be vector 0 because S is empty, so there is no vector for which this is non-zero. That means for every vector this thing is 0. So for every vector, if this inner product is 0, that means this sum we can define only to be 0. And secondly, if S is empty, that means there is no such vector EI for which X EI is non-zero, sorry. That means, and secondly, if this summation is 0 and then we will put the value of summation here, then this X minus this summation becomes X minus 0. And X minus 0 is just the vector X. And since S is empty, so there is no vector EI for which X EI is non-zero. That means for every EI, X EI is 0. That means X is perpendicular to EI for each EI. So we can write X is perpendicular to EJ for each J because this is empty. So there is no vector EI to which X is not perpendicular. It means X is perpendicular to all of the vectors. So this left hand side becomes X when we define this summation to be 0, and X is perpendicular to EJ for all J. That means the theorem is proved for the case when S is empty. And when S is finite, we have proved this case already in theorem A. Now we will assume that S is countably infinite. When S is countably infinite, let us list the vectors of S in this order: E1, E2, E3 and so on up to En, and then so on. Now we put Sn is summation X EI varying from 1 to n, which means the partial sum for this summation, let us take that is Sn. And then for any integer m which is greater than n, we will calculate this norm of Sm minus Sn square. So by definition, this is because Sn is the sum of these terms from 1 to n, and Sm is from 1 to m, and m is bigger than n, so this difference will be just sum of the terms varying from n plus 1 to m xei ei. So we will open this norm square. So norm square will become just inner product of the vector with itself. So when we open this, it will become I varying from 1 n plus 1 to m xei summation I varying from n plus 1 to m. This factor will come outside as such, and this factor will come outside as the conjugate of this vector, and then ei. Now we know this ei, this is orthonormal set, so this inner product ei, this is just 1. So it will be just I varying from n plus 1 to m xei into xei conjugate, that is just mod of this square. So Bessel's inequality shows that summation n varying from 1 to infinity mod of xei whole square, that is less than equals to norm x square. So it is a convergent series. So if that is a convergent series, now here we see that this Sm minus Sn whole square, that is equal to this. This is basically difference of partial sum of that series which we have used in Bessel's inequality. If that series is convergent, that means this is a Cauchy sequence. So from Bessel's theorem, now since Bessel's inequality shows that summation this series is convergent, therefore Sn is a Cauchy sequence in the Hilbert space H. Now Hilbert space H is complete, so this series is convergent to some vector. So there exists a vector S in H such that Sn converges to S. So Sn is, by definition, Sn is sum from 1 to n of the inner product xei into ei. So it means S, which is the limit of Sn, can be written as n varying from 1 to infinity xen into en. So now we define, because now we have proved that this series is convergent and its sum is S, so we can define in this theorem the sum xen to be this summation n varying from 1 to infinity xen en. Now what happened to this summation when we rearrange the vectors of S? So we will firstly we observe that x minus summation xei ei ej, because we want to prove that this vector x minus summation is perpendicular to ej. That means we want to prove this summation, this vector and ej, their inner product is 0. So we will prove this. Now this summation we have defined to be S, so we can write it S. So this becomes x minus s ej. So this is x ej minus s ej. So we can write it x ej minus, now s is limit of Sn, because we have proved here Sn converges to S. So this becomes x ej. Now inner product is jointly continuous, so we can take the limit outside. xej. Now limit of Sn ej, this is just xej. Why this limit is equal to xej? So I'll tell you here. Limit of Sn ej, that is limit of Sn is finite sum I varying from 1 to n x ei. Now product with ej. So this is just limit of, now when we open this inner product, it will become x ei, I varying from 1 to n ei ej. So this ei ej, all these are 0 except when I is equal to j. Now in this summation I varying from 1 to n, the term where I is equal to j, only that term is left, because all other terms where I is not equal to j, this inner product will be 0. So the term where I is equal to j, that will be just x ej, and that is left only x ej into ej, which means 1. So x ej. So that's why this limit is equal to x ej. So we have proved this inner product is 0, which means x minus summation x ei, this is perpendicular to ej for all j. So now we have completed this theorem, except the part that if we rearrange the vectors in S, in the set S, then what will happen to this summation? Because we have proved that if we arrange the vectors of S as e1, e2, en and so on, then this sum is defined to be this, and for this summation we have proved the result. So let us say the vectors of S be rearranged in this manner. Let the vectors in S be rearranged as like this: f1, f2 and so on, fn. This f1, f2, fn, this is just a rearrangement of the vectors e1, e2, en. So now we put another partial sum Sn dash. This is I varying from 1 to n x fi, as we have defined Sn earlier. Similarly we define Sn dash. So for the above procedure, as we have proved that Sn is Cauchy sequence, and then there exists some vector S to which the sequence converges because this is a complete space. Similarly we can prove here also Sn dash is a Cauchy sequence and it will converge to some limit, and let us say Sn dash converges to S dash. That means this S dash, that can be written as summation n varying from 1 to infinity x fn into fn. So we will prove that S dash is equal to S. That means if we rearrange the vectors in S, then their sum will not be changed. This S is capital S, this is for set, and this is small s, this which is actually a limit. And this. So we have to prove S dash is equal to S. So let us give an epsilon, and let us take n naught to be the positive integer, n naught to be the positive integer, n naught to be the positive integer such that if n greater than equals to n naught, then since Sn converges to S, so Sn minus S is less than epsilon, and secondly Sn dash minus S dash, this is also less than epsilon. Now we know, because Sn converges to S, Sn dash converges to S dash, for a given epsilon we can find n naught such that this is less than epsilon, this is less than epsilon for all n greater than equals to n naught. So it means now S dash, sorry, S is summation of x en from 1 to infinity, and Sn is summation from 1 to n. So when we take the difference Sn minus S, then its summation will be n to n plus 1 to infinity. So it means summation I varying from n naught plus 1 to infinity mod x ei whole square, this is also less than epsilon square. This is because Sn minus S is less than epsilon, so square of this norm is less than epsilon square. Then square of norm can be opened as inner product of the vector with itself. So this thing is true for Sn naught minus S. So from the vectors n naught plus 1 to infinity, जो inner product that if you simplify that inner product, that will become just this summation, so that will be less than epsilon square. So for any positive integer m naught, for some positive integer m naught which is greater than n naught, we know all the terms of Sn naught occur among the terms of Sm naught dash, because Sm is just the rearrangement of Sn. Sorry, Sn dash, this is just the rearrangement of Sn. So that means all the terms of Sn naught, they occur somewhere in Sn naught for some integer m naught. So it means the difference Sm naught minus Sn naught, this is just a finite sum of terms. Finite sum of terms of the type x ei, because this is just a rearrangement, and here I varying from n naught plus 1 up to and so on. So from this we can conclude Sm naught dash minus Sn naught norm square, this will be less than equals to I varying from n naught plus 1 to infinity mod x ei whole square, because we are saying all the terms of Sn naught occur among the terms of this, and we know this difference, that is just the sum from n naught plus 1 to infinity, and the terms which occur here also, they will be cancelled in this difference. So this particular norm is less than equal to this, and this we have already proved less than epsilon square. Therefore we can say Sm naught dash Sn naught, this is less than epsilon. And secondly, now we start S dash minus S. Now this is S dash minus Sm naught dash plus Sm naught dash minus Sn naught plus Sn naught minus S. So we have just added and subtracted the terms Sm naught dash and added and subtracted the terms Sn naught, and then we have applied the result that norm of sum is less than equals to sum of norms. So this is less than epsilon, this is less than epsilon, this is less than epsilon. So this is less than 3 epsilon. Now epsilon is arbitrary, and we have proved s dash minus s is less than epsilon, which means s dash is equal to s. That means if we rearrange the terms, rearrange the vectors of the set S, then the sum of the series Sn, that does not change. So it completes the proof of the theorem. Now we know if H is a non-zero Hilbert space, then the class of all orthonormal sets, that is non-empty. Because if H is a non-zero Hilbert space, then at least it has a vector, let us say x, which is non-zero, and if x is there, then x upon norm x, that singleton set that forms an orthonormal set. So there always exists orthonormal set for this kind of Hilbert space. That means if we take the collection of all orthonormal sets, that is non-empty. So now we will make this collection of all orthonormal sets to be a partially ordered set, and we define here a relation which is just the inclusion. So firstly, we define complete orthonormal set. So complete orthonormal set is that orthonormal set which is maximal in this partially ordered set, which means it is impossible to add a vector in such a way that the given orthonormal set, after adding that vector, that is still an orthonormal set, which means it is the maximal orthonormal set, means no bigger set than this set will be orthonormal. So firstly, if we take H to be a non-zero Hilbert space, if H is non-zero Hilbert space, then there exists always an orthonormal set. That means the collection of all orthonormal sets that is non-empty, and we define a relation, and let us say this collection is F, a relation on F by S1 is less than equal to S2 if S1 is contained in S2, where this S1 and S2, they are orthonormal sets of the Hilbert space H. That means they belong to the collection F. So this relation can be proved to be a partially ordered set, which means it is reflexive, antisymmetric, and transitive, and that you can prove easily. So this relation is a partial order on F. So now we define complete orthonormal set. So an orthonormal set, let us say EI in a Hilbert space H, this is said to be complete if it is maximal maximal orthonormal set. That means no superset of this set is orthonormal. So we will prove now every non-zero Hilbert space contains a complete orthonormal set. So we have written here that if H is a non-zero Hilbert space, it always contain orthonormal set, but it always contain a complete orthonormal set. So let us prove that. Theorem E. Every non-zero Hilbert space contains a complete orthonormal set. This is actually very easy to prove. This we can prove by Zorn's lemma, because since we have shown that collection of all, so in this theorem we take the collection of all orthonormal sets, and we know for a non-empty Hilbert space this collection is non-empty, and we define a relation, then that relation is a partial order. Then in this partially ordered set, if we can prove that every chain has an upper bound, then by Zorn's lemma it has a maximal element. So let us take a chain, any chain in this collection F. So the union of all the members of that chain, that is just upper bound. For any chain in F, the union of all the members of that chain, that is just upper bound of that chain. So we can apply Zorn's lemma, which says there exists maximal element in this collection F, and that maximal element is our complete orthonormal set, because by Zorn's lemma it is maximal. So it is impossible to add any other vector to this orthonormal set, and that orthonormal set is our required complete orthonormal set. So that you can write yourself. So I'll prove now theorem F. Now if H is a Hilbert space and EI is orthonormal set, then we have these equivalent conditions. The first equivalent condition is that orthonormal set EI is complete. Equivalent conditions. The first one says EI is complete, and the second is X is perpendicular to EI if it implies X is 0. Then third is if X is any arbitrary vector in H, then X can be written as, if X is any vector in H, then X can be written as summation X EI. And fourth is if X is any vector in H, then norm X square, that is just summation of mod X EI whole square. So we have to prove these are equivalent conditions. Now in this theorem, this fourth condition, this is just Parseval's identity, which means you can, if you have to prove Parseval's theorem, then you have to prove if EI is a complete orthonormal set, then for any vector X in H, this norm X square is summation mod X EI square. So firstly we prove 1 implies 2. So in 1 we have given EI is a complete orthonormal set, and secondly we have to prove if X is perpendicular to EI, then X is 0. X is perpendicular to EI means X is perpendicular to all the vectors EI, then X is 0. Now suppose suppose this second condition is not true. Let 2 is not true. Let 2 be not true. So we are saying if X is perpendicular to EI, then X is 0. So suppose there exists a vector which is non-zero and which is perpendicular to EI. So let X is non-zero vector in H such that X is perpendicular to EI. So now we define a vector E, which is X upon norm X. Now since X is non-zero, so this is non-zero vector, and when we divide X by its norm, the norm will be just 1. So we can observe that the vectors EI along with the vector E, means if we add this vector E to the given complete orthonormal set, then this is also orthonormal set. Because x is perpendicular to all EIs, then E will be perpendicular to EI for all I, because E is just x divided by its norm. So E is perpendicular to all the EIs and norm of E is 1. So this is still an orthonormal set. But we have in the first part that EI is complete orthonormal set, and definition of complete says that no vector can be added to this complete orthonormal set to find an orthonormal set. So this is a contradiction. So it means 2 is true, which means x is 0 if x is perpendicular to the set EI. So now we will prove 2 implies 3. Now by previous theorem, theorem D, we have proved here x minus summation x EI, this is orthogonal to the set EI, because in that theorem we have proved x minus summation is perpendicular to EJ for each j. So if it is perpendicular to EJ for each j, that means it is perpendicular to the set EI. And the second condition says if some vector is perpendicular to EI, then that vector is 0, which means this x minus this is 0, which says x is actually the sum equal to this. So now 3 implies 4. Now we start here from norm of x, because we have to prove norm of x square is equal to this. So norm of x square is just the inner product of x with itself, and x is equal to this in the third part. So this becomes now we simplify this inner product. EI actually we can write here this summation is over I, this summation is over j, to avoid the confusion. So this summation can be taken as such outside, this summation can be taken as conjugate of this, then we have EI EJ. Now we know EI, this is orthonormal set, so EI EJ this is 0 except for I is equal to j, and when I is equal to j, this summation, this is just summation I x EI into x EI bar, so it is mod x EI whole square. So this we want to prove in the fourth part. Now 4 implies 1. So we have to prove now EI is complete. So let us say EI is not complete. So if EI is not complete, that means it is proper subset of an orthonormal set. If it is not complete, that means some vector can be added to this, and still it will be orthonormal set. That means we can say this is subset, proper subset of some orthonormal set. Let us say EIE. Now since we are saying this is orthonormal set, that means E is perpendicular to all EJs. So it means norm of E square, this is by fourth part. We have said that for any vector x, norm x square is just a summation of mod of this inner product square. So norm E is just summation over I EI whole square. But also we are saying that E is perpendicular to EJ for all j. That means this inner product is 0 for every I. So if this is 0, that means it is 0. So norm of E square is 0, means E is 0. But we are saying that this is unit vector because this E is a part of orthonormal set, so it is a unit vector. But also we are proving E is 0, so this is a contradiction. It means this must be a complete orthonormal set.